Van-Waals equation state. Which is that R, we can write it as the compressibility factor is PU over RT, and that is equal to V minus V minus A over R E V.
When we spoke about the limitations of that equation, it was it's a famous equation because it takes someone over and directing scientists' attention to the fact that it could be better than the ideal gas, which we know has serious weaknesses. This is a cubic equation that we talked about previously, cubic in the body. It has two adjustable parameters. There are better equations of state that are, some of which are based on it, and I will just mention three of them. Modified Van-Waals equations of state. The Redox-Long equation resembles this notation and oh, I see. That was Z, all right. That was Z. I wanted to write it as well. Let me just change this expression. And that is equal to RT over P minus P. And that is minus A. Okay. I'll say it will be square. So let's go ahead and put this in that notation. RT over V minus V minus A over the square root of T times molar volume times molar volume molar volume. So what these guys have done is tweaked the equation. The A and the B here are not the Van-Waals A and B, they're A's and B's again when you take this form and fit it to the data.
Then there's the Solve A equations, modified Van-Waals equation state. Here, this is a function of temperature. I won't write function out, but it gives some softness to the potential wall, the repulsive wall, and then it too is U plus P. And then there's oh, I'll just mention as I put work. Nope. Now,
one goes like this, it's RT over V minus P, I'll have that lead current, and that is not a function of temperature, a different function than in this law A. And down here we have V squared plus 2V times V minus the V squared. There are numerous others that are in the literature. These are sort of workhorses. I don't think any of you engineers will be probably much more familiar with them than I like this one a little bit because Don Robinson, a friend of mine, and he and I worked on some of the same problems. We were collaborators, but we did some similar work. Unfortunately, he's not with us anymore. He was a fine chemical engineer out of Canada, University of Alberta. So, how do these equations differ from the van der Waals? If we look at the potential energy function, related, its derivative is the force function we talked about. Van der Waals equation, or the force function, would look something like this. We'd have to choose a form for that attractive force, and I should remind you that I posted on the web some days ago, and so on our homepage, you can click to it. There's some notes on the electric force and talk about this attractive force and repulsive forces. And I want to go there and look at them. I won't go into that right now. So that's the van der Waals. These others all have potential to look like this. And that's what our intuition tells us is far more realistic. Now, of course, exactly what that is depends on these parameters. Van der Waals equation, we've already derived that, developed that for first principles. So consequently, these can do a better job of replicating PVT behavior of gases, and they also will allow for condensation, account for that, and they also follow corresponding states. So they're very powerful tools in the weaponry for studying gases and liquids. Now, how about other equations of state? Are there any? Yes, there are a whole slew of them. I'll mention just some of the prominent ones in the development of this science. Equation state, the Ricci equation state, one that I'm particularly fond of. The other one is the Beatty Bridgen equation state. The reason that I like this was my mathematics professor. And, so if you don't like anything I tell you, we start studying thermodynamics, you can blame it on this. So, and one other that I want to mention and dwell on some today. And the idea behind this next type of equation state was suggested by Camberley Otis. And Hunt equation state for which the compressibility factor is equal to a series expansion in the molar volume or the pressure. It could be written down either way. So if we look at the expansion, actually reciprocal volume, it would go like this. Z is equal to 1 plus a function of temperature divided by the molar volume plus a function of temperature divided by the molar volume squared plus ad infinitum. It's a series. Power series. B of T is called the second Fourier coefficient. And incidentally, these are called Fourier equation states. So B of T is the second term. This function of temperature, whatever it is, it's called second Fourier coefficient. Next one is called the third Fourier coefficient. That's first, second, third. Well, what's the first Fourier coefficient?
1.
Thank you. Excellent. This one. Now, why would we be particularly interested in this form of the equation of state? Well, ask a question I want to answer also. And it is because in the theoretical study of gas behavior by statistical mechanics, statistical thermodynamics, statistical methods, it is shown that the first term in the real equation gives the contribution to the compressibility due to the molecules acting independently. That's in an ideal gas. The second term gives the contribution to the compressibility due only to pairwise collisions. Only when the molecules act one on one. And is clearly a function of the forces between the molecules as they come together. In the van der Waals equation, there is no force until the pink they hit and they don't spark. These others, there's attraction and then there's repulsion. So that's beautiful. This term accounts for 3-body collisions. Crystal. Next one took 4-body collisions and 5-body collisions and 6-body and 7-body collisions. And when do you get into situations where higher order collisions are liable to occur?
Higher pressure?
Absolutely, high densities, really high densities. Molecules have to be close together in order for more than 2 of them to interact at that time. We've only never got the air in this room, the molecules move very fast, but they have to move many times their own effective size before they encounter something else. So the chances of them being in real close proximity, but more than one other, get a roll in the program. Nonetheless, that's the beauty of it. And furthermore, statistical mechanics really shows that these terms have the interpretation. I just suggested they do. It shows that the second Fourier coefficient, which accounts for the effects of pairwise collisions, and is equal to the excluded volume per mole due to pairwise collisions. And we know what that is for hard spheres. But the statistical mechanical theory gives this result. I'll just write it out. Minus 2 pi Avogadro's number times the integral from 0 to infinity of e to the minus the potential function r divided by kt minus 1 times r squared times dr. Now, you would develop this equation in advanced courses. And I'm not going to walk you through it like I did through the Magnus equation. And why would I even put it up? Well, because through it we can get some vision. We can peek through the little hole, which on the other side of the window, some marvelous science can take place. And we can make that somewhat comfortable if we try real hard. So this is a theoretical expression. It says that the secondary coefficient depends on the potential energy. Just erase that curve over there. Depends on all whatever that curve is. This one. Well, it also suggests that if we measure these things experimentally, which we can do that, they just come from, yes.
Is right next to the dr, is that an r squared or v squared?
R squared.
R squared. Thank you.
These can be determined experimentally. You measure the compressibility factors and you express the compressibility in the variable notation. Then this term here is going to be the experimental secondary coefficient. So we know about these. We know 2 and pi. We know Avogadro's number. And R is just a measure of, it goes from 0 to infinity. We know about that. The only thing we don't know here is this potential. And I'm suggesting if we measure these, we can make inferences about this. That would be nice. But what we've done is arm waiting about it. So let's see how that would go. Well, I think I'm just continuing the numbering system I was using yesterday. If so, I'll just put a pin on that. That's what we got. Well, as I say, it's not appropriate for us just to pull an area equation out of the hat and say we're going to use this. Not in the course for trying to present science as a defensible set of arguments about how things work, because we haven't proved that at all. So rather than derive it, let's look at an example that we already know the answer and see if it gives us the right answer. If it does for that, and then we can be somewhat comfortable with just going the next step and applying it to the Van Waals equation, which we can represent. So, all practical equations are stated. Can be transformed into imperial notation. So let's look at an example. Of course, in ideal gas is in virial notation. Ideal gas is Z is equal to 1 plus 0 plus 0 plus 0 plus 0 ad infinitum. And why are those other terms are zeros? Because there are no two-body cruisers, there are no three-body cruisers, there are no any-body cruisers in ideal gas. And the 1 accounts for the molecules behaving independently, the ideal gas. Along all of that, what was the next simplest model we looked at? I call it the large model. Nobody else, I'm probably the only man in history, calls it that. But this stands for non-attractive hard spheres. And that was the second model we talked about when we said that the force and the potential both look just like this. Here we have two of those spheres coming together, separated by distance r. They hit. This force moves up like that to infinity. This is the potential function r. This is r, and that's it. We developed that equation state, for which equation state was what? It was P V minus V is equal to RT. You go back and review that, it's in your notes. Pretty easy. We took the ideal gas law, said now how do we have to modify this to account for some size of the molecules. No interaction other than bumping into them. And say, well, you got to diminish the volume by somehow. As we just calculated what that would be for pairwise collisions, we got that 2/3 pi in cube. So we know that. That's not virial rotation. So let's write P, V, RT, that's a Z. Let's see what we get here. Well, I think we get V over V minus V. Is that in virial notation?
No.
Is it? It is not. It is not virial notation. I said all practical equations of state can be transformed into virial notation by mathematical means. And if you remember in your probably calculus course somewhere where you study series expansions of things and solve a whole mess of them, I've got some. See here, I have some just copied out of one of my old math books, and I've got some binomial series, and some Taylor series, and Farag series, and so forth. And I have to assume that you're familiar with those, and that makes me think that those math tables find and use those expansion series. And they're all given with their ranges of convergence. So I'm going to say, recall, math professors will be happy if you do, the binomial expansions, which there are a number, and the one that I want to use. Down here. There's 1 over 1 minus x is equal to, that's the one that I'm sure I want. It's equal to 1 plus x squared plus cosmology. Now I'm going to take that C is equal to V over V minus V and put it in that form. Well, the way we do that is divide the denominator by V, 1 over 1 minus V over V. And then if we let x equal to E over V. Then Z becomes, what? It becomes 1 plus V over V plus 3 squared over V squared plus Gaussian, and that is realization. So this is real. And clearly, for NAR's model gas, V of T is just equal to V, not a function of temperature. It's a constant. And we showed that A is equal to excluded volume per mole due to pairwise collision, which is equal to volumes 2/3 pi and sigma q. That's for large spheres. We're talking about large spheres. That's what the RS stands for. This is sigma. All right. Let's see what in the world our theory says. Times and crack color. We'll write out R squared R. Okay? So, yes.
Hi, for NAR S, I was wondering what does that say? It's on the left.
Right here?
Yeah, for NAR, what's
For NAR's a gas. I don't know what it says. It's supposed to say gas. Okay?
It's okay.
For NAR's model gas, whatever you should say. Collection of non-attractive rigid spheres. Okay? All right. And let me point out something. I told you to be on the lookout for Boltzmann's factors. I told you to be seeing them everywhere in science. What the hell is this? That's a Boltzmann factor, even minus some energy over kT. Potential energy in this case over kT. We saw that in the parametric formula calculation. We saw it in the Parham's grounding motion studies, and you will see it everywhere. We saw it in the actual Boltzmann distributions. Okay, so there it is, and all of its prettiness. Well, so for there it is. This equation becomes A of B is equal to minus 2 pi alpha integral. Okay. What is this potential bus? So have it drawn over here. You write it down. You send your notes to the person. Here it is. U of R is equal to infinity at R at 0 is equal to less than R we had here. So we'll do it piecewise. We'll go from 0 to sigma of e to the minus infinity. I don't need to divide it by anything because infinity will hold up really finite. Divisor. Minus 1 times r squared dr. And then there's the rest of this minus 2 pi n integral from sigma to infinity of e to the minus 5. E minus u, what's u? If r is higher than sigma. 0. E to the minus 0 minus 1 times r squared dr. Boy, it's getting a lot easier, you see. And a whole lot easier. All right. Okay. So we'll take these over here and just notice that that's first term is over minus 2 pi Avogadro's number times integral from 0 to sigma of, okay, what's this? What's e to minus infinity?
0.
Thank you. So it's minus 1 plus 0 minus 1 times r squared dr.
Negative sigma. Sorry. 0.
And then the second term is minus 2 pi integral from sigma to infinity of e to the 0 minus 1 times r squared dr. Okay, so this one's minus 1. What's this?
0.
Thank you. 0. So we can throw that away. And all we've got left is just this. And so that's p of t minus 2 pi Avogadro's number times minus integral of r squared dr comes from 0 to sigma. And that becomes minus plus 2 pi Avogadro's number. And this is r cubed over 3 evaluated from 0 to sigma. And that is 2 pi Avogadro's number times sigma cubed over 3 minus 0. Oh! Theoretical value we get for the second order coefficient. This will be a weird equation we pulled out of the hat. Turns out to be 2 pi Avogadro's number, 2/3 pi Avogadro's number times sigma cubed. But with v and t we get experimentally is 2/3 pi Avogadro's number times sigma cubed. And that's why I feel somewhat justified in using this equation to look at the Van Waals, using this theoretical equation to look at what it suggests about the Van Waals equation. Any question about that? Well, that's my equation 12. We'll find that I'm lost somewhere. It's all right. I mean, I'll see it come back to the result.
This
And look at
theory.
it. So by simple geometric means, we got this. The pictures of the spheres colliding, talks about the sphere of influence. By simple geometric means, we got a result that's exactly what the theory produced. This is the excluded volume for normal Euclid solutions. is show off the road to the Van Gogh equation. Sorry, that's equation, so it's better than the Norris equation. And it has some attractions, which I guess softens the sorriness of it. And those attractions are probably what we'll look at. We're going to have to transform the Van-Gogh equation to zero form. So the Van-Gogh equation is, did I write down the, C for earlier, I think I did. Like that, right? That's not zero notation. So how are we going to get there? Well, this term here is just 1 over 1 minus p over v, which we already know what it is. We saw that a minute ago. And that is just that's 1 plus p over v plus v squared over v squared plus almost. So we've done that part. And we've not done it all. So the C Van Gogh is equal to 1. Now let's get the terms that have the molar volume and the denominator. And there are 2 of them. There's this one and there's this one. So we can say plus v minus a over r t over v plus v squared over v squared plus v cubed over v cubed plus 1/7. So we say we now transform Van Gogh's equation into zero form. This counts for departures from ideality to pairwise solutions. And it's not as simple as it was when they were with no attraction. Here's where the attraction traits are overhead right here. All right. So therefore, that is v minus a over r. So, I don't know if I know that or not, but I should have been. Yeah. Question 13. Now the question is, will depend on that Van Gogh's potential. Which has this form again. Now the notes on the numerical force and electric potential, which I posted on the web, I talk about a realistic potential that's widely used in calculations theoretical pursuits for pairwise collisions. It's called the Lennard-Jones potential. The long range attractions here, which derive from, now let me back up, tell you this. Every pair of molecules, no matter what they are, when they get close together, attract one another. It's in, even if they're ions, even if they have the same charge, they're still an attraction. It may not be as big as an electrostatic repulsion, but neutral atoms always feel attraction, no matter. And that derives from the polarizability of the molecules, the displacement on average or the center of negative electricity from positive electricity. Even the molecule doesn't have a proton dipole, it's going to get a transitory dipole. Just walking around doing it all the time. And when you bring two together, the dipole, instantaneous dipole on one induces an instantaneous dipole on the other, and vice versa. They're like hermaphrodite worms that fit one another. So they're always, on average, sometimes they're pushing, sometimes they're pulling. On average, it's pull more than push. And those are dispersion forces, and they're pretty well understood theoretically, and they go like this. This potential for dispersion, U of R is a minus sign plus subtraction, a constant with a sub 6 on it, over R to the 6th power. And this is called the Sutherland potential. There are lots of names it goes by. London dispersion forces, Sutherland potential. But we're identifying a reasonable guess at its form. And it's actually based on pretty good theoretical knowledge about several molecules. Now, if they're polar molecules or other forces. So let's use this as our best guess. Now, down here, this what we call a potential well. Like a skateboarder comes down here, runs into a wall there, and spirals. Bottom of that well. And its depth down here is at minus C6 over sigma 6. Depth of that well, it's just where this energy stops right there. It's gotten down to C minus C6 over R over sigma 6. So what we hope to get out of this is our target to find out something about how big these forces are. Put a number on it. We already know what sigma is. The molecules we extract that from the van Ross B constant. But we don't know anything about how big these attractions are. It's important. So we can get a feel for it without being real serious big time theoretical chemists, just finding it in very common knowledge. Really easy to understand now. So let's do that. What we do is we calculate theoretical theoretical secondary coefficient and compare it to that. And make the logical fit to crime. So let's see. And how would we characterize this potential over here? We would say that U of R equal infinity between 0 and sigma, and U of R is equal to minus C6 over R6 or R is greater than sigma. That's right. So deity, Van Laws, theoretical equals, well, it's minus 2 pi. When I integrate this piecemeal again, we're going to go from 0 to sigma, and it's e to the minus U of R over KT minus 1 times R squared dr. But this, I've already said, is how much? This is 0. Huh? You've already infinite. This is exactly, we're doing the part of a non-tracking sphere. That's what's, so this is, I have just minus 1 R squared dr, we know that one. And the second term is minus 2 pi Potter's number, the integral from sigma to infinity of e to the minus e to the plus c6 over kt r to the 6. Now find out for the plus sign there. Because u r is u of r is minus c6 over r. So minus u of r is plus c6 over r. Minus 1 times r squared dr. Do we know this first term already? Do we have to recalculate? Do we know what it was? This is the same integral we got. We look at the non-tracking R squares. This is the integral of R squared dr. It's R cubed over 3. Minuses cancel out. We know what this first term is. It's what? It's 2 thirds pi and sigma cubed. And what's another name for that? Little b, van der Waals b. So we know that one. And then we have minus 2 pi and times the whole plot. Integral from sigma to infinity of e to the plus c6 over kt r to the 6 minus 1 times r squared dr. So all we have to do is integrate this sucker and we're home free. And we can do that, but these forces are weak. And the molecules don't get close enough together. Don't get close enough together to feel this infinite force. The R spheres go apart. But these forces are. So consequently, we can expand e to the c6 over kt r 6 pi. Expand that in one of our little series over here, and that would be in the farm series. For which e to the x, if I look what this one is now, e to the x is equal to 1 plus x squared over 2 factorial, etc. Now if x is less than 1, it is here, it's small, what happens? These terms diminish rapidly. We can truncate the expansion after the second term. So we just keep that much of it. second term. We get this result here. And that is that, integral sigma to infinity of e to the minus, it's called x now, because we're going to let x be. The x be c to the 6 over kt r to 6. E to the minus x times 1 r squared dr becomes integral of becomes the integral of x 1 plus x minus 1 times r squared dr. That becomes the integral of just x r squared dr. So that's how we simplify this. And if I do that, done with this, then we have A, B, and false theoretical. That comes little b, that's our first term, we've already evaluated that one, minus 2 pi n integral from sigma to infinity of just, all we have to keep is the argument of that exponent, and that is a to 6 over k d r to 6, and that is r squared r. So that's minus 2. That's b minus 2 pi n. Take out the constant terms, c to the 6 over kt, and we have the integral from sigma to infinity of r to the minus 4 dr. And that's looking more manageable. And that is b minus 2 pi n times c to 6 over kt. And it is just sigma to the minus 3 over 3. Minus 3. And all right. So that is 2/3 pi n. Got C6 over sigma cubed kt. Of course, that was just 3 up here. All right. So let's multiply and divide by sigma cubed. And if we do that, we get a minus 2 pi n sigma cubed times c to the 6 over sigma to the 6 over 2.
Why isn't it plus b plus and then the rest
Beg
of it?
pardon?
Wouldn't the minus from the -3 and the minus after the b cancel out to be a positive?
This one I'm talking about this one.
Yeah,
Yeah.
That just been carried along from right here.
right. But when you did the integral, it put a -3 in the denominator. So the
Oh, yeah.
Oh,
so this is
you're
plus.
doing a definite integral, so you're using the second term. So it's minus the sigma.
Right,
This-
but
this-
yeah,
this
we're
process.
saying when you did the integral, it was sigma to the -3 over -3, and that -3 would change the
That's
minus.
Right, and then but when you plug in the sigma, right? When you do the definite integral, fundamental theorem, you do
Where-
infinity
Yeah.
term and then minus the sigma on both.
Yeah,
And since it's a cube term, it keeps
that's
it,
exactly right.
Gotcha.
it keeps it signed.
Okay,
Yeah.
gotcha. All right, thank
Now,
you.
you just go through this methodically. I was planning on having all that now, I think back.
No, that's a great point.
So, alright. Compare this
Yeah. So it's supposed to stay minus.
Yeah, because it's
to
0 minus that.
A of the experimental, which is equal to B of, as it was, and I gotta be sure I got this thing right. Fixed all. Okay. B minus, it was A over R T. Okay. So if that's the case, I got a sign there wrong somewhere.
No, that's supposed to be a minus sign.
Yes, it
Yeah.
is. Yeah, I'm pretty sure it is. So we compare these two, this term and that term have to be equal. So we got that, 2 pi. Should be a 3 in here somewhere, we'll do that. Alright, this is B again. So we get B times C6 over sigma 6 over KT is equal to A over RT. The T's cancel out. That's looking all right. Oh, that's right. So we'll get C6 over C6 is equal to A times K over R. See a B here somewhere, where that at? Always have this B here as well, and so it is over BR. There we go. Alright, so that's what we got up here, A over BR. Now, we write that as A over B times R over K. We know what that means for it. The gas all constant on a molar basis, and the gas all constant on a motor basis. So what does that mean? That's our quadrant. So, after saying a lot of them, I believe just a minute, so let me just tell you this. First place, none of this is going to be on the test on Friday, okay? None of this, none of I talked about today is going to be on the test on Friday. But we're going to come back and visit again next week, and we're going to finish up this fall, this important part. Is that we now have an equation that gives us this C6 constant in terms of sigma, A, and B. B is proportional to sigma. And we can put numbers to it. So we can say that the pool is this many units or that many units or whatever. The depth of that well is this many joules or that many joules, whatever. And that's very worth knowing about. So come to class on Monday and we will revisit this and get down to that and very shortly then get on to our next topic, which is number 9. Sorry about the confusion. for today. And, the two of you who needed these papers filled out, we took them yesterday, if you're here, I don't know how time you usually have.